Hello everyone, in this video we write 4 functions to compute the Fibonacci sequence. And we are going to use two different approaches. For the first 3 functions we are going to use dynamic programming, and for the last function we are going to use vectorization. So first of all, what is the Fibonacci sequence? The Fibonacci sequence is this series of numbers where the next number is found by adding up the two numbers before it. For example, 2 is equal to 1 plus 1. 3 is equal to 2 plus 1. 5 is equal to 3 plus 2, and so on. Starting values are 0 and 1, and no negative input is allowed. Let's write the first function by using a dynamic programming, a naive approach. So basically, we write this function, Fibonacci takes one argument, n. If n is less than 0, we stop the function and we throw an error message, negative input not allowed. Else, if n is less or equal to 1, we return n. Else, here, we are calling back the function. As you can see, we are calling back the function here. And this is the recursive approach. Let's run and let's test it. So input -1, we get the error message, negative input not allowed. Let's go for 0, 1, and let's compare with the sequence, and that's it. Okay, so now the function is returning the number for the n term. Let's say that we want all the sequence up to the n term included. What we need is just the supply function for this. This is the function that really matters, but we are wrapping this function in this Fibonacci underscore sequence. So let's run here. Now let's build this vector from 0 to 6. Let's give this to the function. And as you can see now, we get all the sequence. Let's go for 0 to 10. And now from 0 to 30. And as you can see, the function now is slower. What is the issue? The issue is with exponential time. Let's check it. For example, let's say that we want to compute Fibonacci 5. So Fibonacci 5 is equal to Fibonacci 4 plus Fibonacci 3. But Fibonacci 4 is equal to Fibonacci 3 plus Fibonacci 2. Fibonacci 3 is equal to Fibonacci 2 plus Fibonacci 1. What is the issue is that if we compute this Fibonacci 3 here, we should not need to recompute again, but in this case we are computing again Fibonacci 3, and the same is for Fibonacci 2, as you can see here and here. Now this example is with 5, but you can imagine if we supply 30 or even a greater number, how many times we recompute the same values. How we solve this problem? With dynamic programming with memoization. Basically, if we compute a value, we want to reuse that value. So if we compute this Fibonacci tree here, basically, we are going to reuse it. This means that we are going not to compute this tree here. And this will speed up the function. Now, this is the function, but it's not mine. I took from the R bloggers. I leave the link in the description. I just made a small change here and I added these comments, but I'm not going to comment this function. I prefer that you read directly from their website. So let's run it. Let's test it. Let's do the same. So let's compute for the sequence. We are using the same approach as before. Let's test it. See now for the sequence from 0 to 30. You see how it's extremely fast. Okay. So now the third function with dynamic programming is the bottom-up dynamic programming. Basically, in this case, we are starting from the end. Okay, so we're computing from 0, 1, and so on. And we're going to use a loop. So first of all, we generate here, we are initializing this object by using numeric n plus 1. Now, why n plus 1? Because the first entry here is 0, but R start indexing from 1. Let's see a case here. As you can see in the loop, for I in 0 to n, if I is less or equal to 1, we return the value I. But let's say that I is 0. If we place 0 here, we will get an error, because as I said, R start indexing from 1. But we can correct this just by adding plus 1. So in this case, I is 0, but this is 0 plus 1 is 1, and it's taking value 0. Basically, we are saying at index 1, give value 0. This is what we are saying. When I becomes 1, this means that I is 1, so 1 plus 1 is 2. This means that we are at index 2. At index 2, assign value 1. Else, so let's say that we are at 2 in the loop. So 2 plus 1 is 3. So we are at index 3. And we're seeing that index 3 is 2 plus 1, 3, minus 1. So here, index 2. And this is 2 plus 1, 3, minus 2, 1, index 1. So basically, we are just saying that this number is the sum of this number and this number, and so on. So let's run. And the way that we wrote this function automatically return the sequence. Let's test it. As you can see, we get the sequence. It also in this case is extremely fast. If you want only the n term, you just do like this. Let's run the function. And now, as you can see, it just return the final value, the n term, but let's reset for the sequence. Okay. Okay, so if you want to know more about dynamic programming with a Fibonacci example, I strongly recommend Introduction to Algorithms and Lecture 19, Dynamic Programming 1, Fibonacci, Shortest Paths by Professor Erik Demaine from the MIT. I leave in the description the link to the lecture on YouTube. Okay, so now we are changing approach. Until now we work with dynamic programming. Now we will deal with the Fibonacci sequence as a mathematical program. So the Fibonacci sequence is a second order difference equation. There are different ways to solve the Fibonacci sequence, and you may encounter one method that uses a matrix multiplication. In that case, that matrix multiplication is the result of a second order difference equation reduced to a system of two first order difference equations. In our case, we are going to use a different approach. We are going to deal directly with the second order difference equation. I'm not going through the math, but just know that I changed the index. I'm just moving forward the index. For example, this is t plus 2 is equal to t plus 1 plus yt. So yt plus 2 is equal yt plus 1 plus yt. And basically, this is what we really write from the beginning. I just replace n with t, but this is n minus 1 plus n minus 2. So you can think that this is n equal or t equal t minus 1 plus t minus 2. In this case, I am adjusting moving the index, but the nature of the problem does not change. So let's rewrite this one. We subtract from both sides of the equation minus yt plus 1 and minus yt. So we have this form here. I use this index t plus 2 and t plus 1 and t because when I manually solve the second order difference equation with the general method, I prefer to use this index. Now, we say that the initial values are 0 and 1. So basically, with initial value 0 and 1, this becomes the particular solution. Okay, so in this function, the argument is t. We are controlling for this t here, but again, this could be n. So let's run and let's test it. Now with only one value, and you can see very fast, and with all the sequence, and again, it's very fast. So let's compare the speed of these algorithms. Let's start with the first one that we wrote. And as you can see, for just one value, it takes 2.28 on my machine. Let's check with memoization, it's 0. With vectorization, it's also 0. So we greatly improved. Let's check with the sequence. Again, we start with the naive approach. And as you can see, on my machine, 5.25. Let's check with the other algorithms. This is 0.01, this is 0, and this is also 0. Let's try with a bigger sequence from 0 to 2000. So this one is with memoization 0.22. This is 0, and this is 0. So which is the fastest? With the sequence up to 100,000. Let's check. 0.03, 0.11. So the fastest in our case is the Fibonacci with the bottom-up dynamic programming approach. So, but are we correct? Let's check for the number 50. So this is our solution. And I'm going on this pari.mat U Bordeaux website here. Right. Fibonacci 50. Evaluate. Let's check if we are correct. Uh, 12, 58, 62, 69, 0, 25, and it's correct. Let's try with the sequence from 0 to 70. And now these are very large numbers, so we have scientific notation, and let's disable scientific notation for this result. We can use two approaches with format, the function here, the number that we want to change, and scientific equal false. These are the numbers. Or we can use this sprint function with this notation and the numbers that we want to change. And here I describe the meaning of this expression here. Let's run. And now let's check if we are correct. And naturally, we just computed the last term, 70. Check. So we have 19, 0, 3, 9, 24, 90, 70, 91, 35. Okay. Now let's check for a large number for 100. So only for 100. This is our result. Let's check it. So we have here 35, 42, 40, 24 here, 85, 81, 79, 26, and as you can see, for these last digits, they are not the same. But this is an issue with the accuracy with these extremely large numbers. I read that the R package called RMPFR should deal with this accuracy problem. Honestly, I did not try because it was outside of the scope of this video. And if any of you tried this package, let me know in the comment if you can obtain the accurate 100 term. So I hope this video is useful and see you in the next video.